So, very good morning to all. My name is Sobhan Pattajoshi. Today I am here to deliver the presentation on the prediction of the dynamic crack path of concrete under projectile impact loading with Dr. Sonali Sare, Professor of Department of Civil Engineering, IIT Roorkee, India. So, here is the basic outline of my presentation. So, to begin with, I'll start with the motivation part, like why we are doing this. So, I'll just turn on the pointer. Yeah. So, in our published article, we have performed the validation for the handcheck et al. Validation experimentation. Actually. So, in this experimentation, we have observed that our numerical results predict the damage, which is actually underestimated. You can see over here, the damage is underpredicted for every case, every CA. So to improve, basically the damage behavior and which incorporates the crack strain itself, uh, so we have decided to proceed further with this improvement in the damage model so that we can improve our damage as well as the dynamic crack path prediction. So to begin with, okay, here is the literature review, so I'll just skip it. So coming on to the work done part, the damage modification basically. So here we have two damage models, basically the shear damage model and the compaction damage model. In the shear damage model, over here, this works in the whole compression pressure regime. Whereas this compaction damage model, this works only under a specific domain of the compression pressure regime. Basically, it works from the crushing pressure to the locking pressure. In the default RST model, these two damages are clubbed as one damage parameter. So we have bifurcated this two damage models, to specify the pressure regimes of the compression part. In the next part, we have, adopted this two damage models which work under the tensile pressure regimes, basically, and this is the hydrostatic expansion damage model. And this damage model, that is the tensile crack softening damage model, this takes care for the improved damage as well as the improved dynamic crack path prediction under dynamic loading. So here we can see this incorporates the ECR, that epsilon CR, that is the cracking stream. And once basically that things we have talked over here is like four damage models. Two works under the compression pressure regime, and these two works in the tensile pressure regime. So these two damage models are not there in the default RST model. That's why the damage that we have seen in the motivation slide were underpredicted. Now we have the four damage models. We want to club it together as a single damage parameter called as D, which varies from 0 to 1. So we have adopted the Pereira et al. Theory to incorporate all the four damage models into a single damage parameter. So once the damage models are finalized, we have proceeded further for the single element analysis through user subroutine in ANSYS Autodive. This is the basic description of the single element. Like we have applied the two fixed support over here and two velocity boundary conditions at the top, and we have also put the gauges to calculate the stress strain, or we can directly get the stress strain plots from here. We can use any of the three gauges basically. Not three gauges are required. So to begin with the single element simulations, first we have performed in the default RST model for both the uniaxial tension over here and uniaxial compression at a strain rate of 1. And we get the stress strain plot of the uniaxial tension and compression as we can see over here. So we are more interested, in the tension regime, tension pressure regime, where we have the stress versus strain plot. So we can see post-peak behavior is almost kind of linear. So we'll talk later about this in the upcoming slides. And once this default single element analysis is done, we have moved to to the user subroutine application in the ANSYS autoline for the initial compression test, and we got the plot over here as this. And after this, we have applied for the tension tests and the numerical simulation of the single element to use a subroutine, applying the modified damage model basically. So here we can see the post-peak behavior now changes to the exponential form. Now this is what we are much more concerned about and we required actually. So we'll see this slide in the comparison actually. So if we see over here in the initial test comparison, and if we see the plots over here, the stress strain plots, so the blue one represents the tension stress strain plot of the default RST model that actually under predicts the damage behavior. That means we have the tension strength is overestimated. So if we see the area under the stress strain curve over here, which is this for the default model, but if we see it for the modified model, so it is nearly reduced to the half. The area of the stress strain curve is nearly reduced to half. That means fracture energy is reduced, and now we can say the under prediction will now get improved, that we will see in the upcoming slides. Basically, yeah. So this is the actually combined plot of the stress strain of the tension and the compression part, basically for both the default and the subroutine model at a strain rate of 1 to have a visualization of of both tension and compression at once. Now moving on to the next phase, that is once the damage model are fixed, single element analysis are done for the stress strain plots to get the validation of the exponential form of the tensile region, and we now validate again the Hanchek et al. Model, and here we see that for both the 48 MPa concrete strength and 140 MPa concrete strength, here we have the results for the residual velocity. This- yeah, residual velocity and the percentage change in both of these are plot. And if we see the damage diameter, the damage diameter percentage variation is much more. That means things are getting changed. The damage, tensile damage. Now this is the comparison, damage comparison for the default RST model. Upper one, this one is for 48 MPa strength concrete, and the lower one is for the 140 MPa concrete strength. If you see this cone going from the front to the rear, this cone is follows the basic concrete cone failure under dynamic impact loading, and similar is the case for the 140 MPa concrete strength. And if we go again back to our motivation slide, actually, we see over here, this was performed in the 3D analysis actually. So here also, if you see for the numerical part, this cone, if you see, the damage is increasing. The damage diameter is increasing from the front to the rear part. That is also valid for the experimental also, if you see. So similar is the case here. But the thing we observe here, that in the experimentation, for the 48 concrete MPa strength in the experimentation, if you see here the damage, this is less when compared to the 140 MPa damage in both the front and the rear. But if you observe in the numerical part, this is coming out to be the reverse, which should not be the case actually, because once the strength of the concrete increases, that we have more brittleness over there. And coming on again to the slide, so here also we see in the 2D numerical simulations basically that the similar thing happened. That this damage prediction is again less in the default one. But when we perform this simulation through the user subroutine by applying the modified damage, so now you can see that in the rear part of the impact of the slab, RCC slab, the rear part damage is now much more, coming out to be what is being seen in the experimentation. Actually, the front part is not coming out to be that much accurate again. But why the rear part is coming accurate? Because we have basically modified the damage in the tension pressure regime, and that occurs at the rear part of the impact loading in the cell, basically. So if I go back and forth, so you can see this one is default, this one is subroutine. So the damage is actually increased. Now moving on to the next slide, that is for the dynamic track path prediction. So from the reference, that is Wareham et al. 2007, they have performed some SHPV tests, dynamic tests, to predict the crack path, and they have, you know, got this kind of a crack path behavior, in which we can see at every increment, crack strain increment, the crack path is dynamically, diverting, changing from its path. It is not at all straight. It is continuously changing its path. So if you observe in the numerical simulations that we have performed through user subroutine, here also we see the similar behavior, that the damage, that is the dynamic crack path, that is continuously changing. That is dynamic. That is not at all straight anyway. If we go to the default, default damage in the RST, you see in the 140 ampere, here it is completely straight. This should not be the case actually. Here some part is straight. In the 48 MPa, it is somewhat okay, we can say. But if we see in the subroutine part, it is totally, improved. The dynamic crack population is totally improved. That is thanks to the elastic epsilon CR, that is the cracking strain rate incorporation in the dynamic tensile damage behavior. Now, this is the animation of the impact simulations for both the 48 and 140 MPa concrete strength. The left side represents for the default model, and the right one represents the subroutine model actually. So you can directly compare. One can directly compare from the simulation parts. So I'll just play once again. So that's that. And next we have this stress wave propagation to the thickness of the concrete in the direction of the projectile motion actually. So here also the left part represents the default model, the right one, represents the subroutine model. So if I play it again and if you see that when the projectile passes through the target, so that is the stress rate is totally tensed. Red means totally tensed. If it is blue, the blue part is the extreme one, that is the compression part. The red one is the another extreme, that is the tension part. So when it is passing, it is completely tense, that is completely red. But once it has passed the target, if we see over here and compare for the 48 MPa strength, once the projectile passes, the stress rate is, if we compare for the 48 from the left to right, going from left to right is going more to the red. That means now the stress predictions, tensile stress predictions, are actually capturing this behavior, capturing that tension part more accurately. Similar is the case for the 140 M. Now the conclusion. So the modified damage model with the incorporation of the cracking strain provides a more realistic depiction of concrete damage as well as the dynamic crack path compared to the default RST model and other recent modifications. It accurately simulates the exponential strength softening under hydrostatic tension, which was a limitation actually. And numerical simulation of the ballistic impact on concrete targets validate the efficacy of modified damage model in reproducing the damage diameter and residual velocity of the projectile. These are my recent publications. These are the references. Thank you so much.